Welcome to the discussion. Today we're exploring a fascinating paper that connects seemingly disparate fields: fuzzy logic, neuroscience, and quantum mechanics. The authors propose a new link between them, all through the lens of Bayesian probability. What initially strikes you as the most intriguing aspect of this connection?
The most intriguing aspect is the unifying power of Bayesian probability. It's not just a mathematical tool, it reflects how we as humans process uncertainty. The paper suggests our brains, with their fuzzy logic like neural networks, operate in a way surprisingly similar to how quantum mechanics, interpreted through QBism, handles probabilities.
That's a bold claim. Can you elaborate on how Bayesian probability fits into this framework? For our listeners who might not be familiar, what is Bayesian probability?
Bayesian probability views probabilities as degrees of belief, constantly updated with new evidence. It's different from the frequentist approach, which focuses on long-run frequencies. In this paper, Bayesian probability acts as the bridge, showing how our subjective beliefs, Bayesian, align with both the fuzzy nature of neural processing and the probabilistic interpretations of quantum mechanics.
So our brains use fuzzy logic. How does that work?
The neocortex, the thinking part of our brain, is organized into cortical columns. These columns aren't sharply defined, their boundaries are fuzzy. This fuzzy set theory, where things aren't strictly in or out of a category, mirrors how neurons process information gradually, with varying degrees of activation.
And how does this fuzzy brain activity relate to Bayesian probability?
The paper argues that the elements of Bayes' theorem prior probability, likelihood, and posterior probability can be represented as fuzzy sets. The brain's updating of beliefs based on new information is essentially a fuzzy inference process.
That's quite a leap. How does quantum mechanics fit into this picture?
QBism, a relatively new interpretation of quantum mechanics, aligns perfectly. It posits that quantum probabilities are also Bayesian subjective degrees of belief held by an observer. This removes the mystery of wave function collapse, viewing it as a Bayesian update of beliefs.
So wave functions are fuzzy sets?
The paper suggests that wave functions and measurement operators in QBism can be seen as analogous to fuzzy sets. The uncertainty inherent in quantum mechanics mirrors the fuzziness in neural processing and Bayesian belief updating.
Are there any existing links between fuzzy logic and quantum mechanics that this paper builds upon?
Yes, there have been attempts to connect the two, often focusing on the similarity between superposition in quantum mechanics and the concept of membership degrees in fuzzy sets. However, this paper goes further by incorporating neuroscience and the Bayesian framework.
The paper mentions the Born rule. How does that fit into this fuzzy Bayesian quantum connection?
The Born rule, which calculates probabilities in quantum mechanics, can be reinterpreted within the QBism framework as a kind of quantum law of total probability, an extension of Bayesian probability. This further strengthens the link between the three areas.
What are the implications of this new connection for artificial intelligence?
The paper suggests that understanding this link could lead to new AI systems that mimic the brain's efficient and robust way of handling uncertainty. It could inspire new algorithms and architectures for unconventional computing.
Unconventional computing. What does that mean in this context?
It refers to computing paradigms that go beyond the traditional digital approach. This could involve using molecular systems or other physical processes to perform computations, inspired by the fuzzy and probabilistic nature of the brain and quantum systems.
The paper mentions the use of molecules in processing fuzzy logic. How could that work?
Molecules can exist in multiple states, conformers, microenvironments, which can be described as a quantum mixed state. The probabilities of these states can be interpreted as fuzzy membership degrees. Changes in the environment can alter these probabilities, effectively processing fuzzy information.
And how can we measure these molecular probabilities?
Techniques like time-resolved spectroscopy combined with the maximum entropy method, MEMM, can be used to estimate the probabilities of different molecular states. This provides a way to quantify the fuzzy information processed by molecular systems.
So in essence, this paper proposes a new interdisciplinary approach to AI and unconventional computing, drawing inspiration from the fuzzy, Bayesian, and probabilistic nature of the brain and quantum mechanics. A truly fascinating concept. Thank you for this discussion.